Now we come to the last step in the process, and that's the actual design of the next state decoder. In order to do that, I need to grab some values from the table in the previous example. Of course, we're always going to choose the inputs to appear in the standard binary order. So we're looking at every possible combination of the inputs, and we're going to put them in the standard order. Remember that on the previous example we did the transitions, conditions, and inputs table. We actually did 3 examples. We're looking at the first example because the other 2 were just other random patterns, but I want to go back and look at the first table. So I'm going to copy the values off of that. That's a 1, a 0, an X, and an X. And then I'm going to have an X, a 1, and a 0. A 1, an X, a 1, and an X, and then an X, 1, X, 1. So again, all I've done here is to copy the first 2 columns and the last 4 columns from the first table that we did in the previous example. Now I'm going to look at each one of these outputs one by one, and I'm going to figure what needs to be done to generate that individual output. And so I'm going to look, for example, at J sub B first. And I'm going to use a Carnot map for this. So I've already got the 4 Carnot maps sort of drawn for your convenience here. So if I want to do J sub B, that's going to be a 1, 0, X, X. And the fewest and largest groups that will circle all the 1s but none of the 0s is to circle the top row. And so when I circle the top row, that corresponds to Q sub A being 0. And therefore, J sub B is Q sub A bar. I'll do K sub B next. That's an X, a 1, and a 0. And once again, the best solution there is to circle the top row. So now it's Q sub A bar. To do J sub A, that's going to be a 1, an X, a 1, and an X. There's no 0s in that table, so I'm going to circle the entire table. That's the simplest solution. Therefore, J sub A is just 1. And then again, X, 1, X, 1. I can see there are no 0s, so I'm circling the whole table, and therefore K sub A is equal to 1. So we've made a lot of progress. We've gone from the table to the Carnot maps, from the Carnot maps to the equations, and now all that remains is to actually complete the circuit diagram. And now we're down to literally the level of hardware where we could actually wire this thing up and see the behavior that we're desiring. Remember that ultimately in the beginning our desired behavior was a modulus 4 2-bit down counter that will go from 3, 2, 1, 0, 3, 2, 1, 0, and we now can make that happen. How do we make that happen? Well, J sub A needs to be 1, so I'll set this to be 5 volts. K sub A needs to be 1, so I'll set that to be 5 volts. J sub B and K sub B need to be connected together. So I'll show a wire here connecting them together. And they both need to be connected. They both need to be connected to Q sub A bar. So I'm going to feed Q sub A bar back in over here, and that connects into both of them. Hardware done. So it doesn't take very many connections, but if we hadn't gone through this full process of doing the step-by-step solution procedure, we wouldn't have known what connections to make. And yes, I'm sure that you figured out by now, this is sequential circuit number 2 from the previous lab that you did, where we in fact analyzed it both on paper and in the lab, and we saw that it does in fact count 3, 2, 1, 0, 3, 2, 1, 0, 3, 2, 1, 0. So we've already pre-verified that this is the correct solution. It's just that we did the verification before we actually did the design. So I hope that helps you to see an example of how to do a design of a sequential device from start to finish. The last example we're going to do is going to do the entire process, this time for a 3-bit device, all the way from the start to the finish.